science. Science has allowed us to know so much about the far reaches of the universe, which is at the same time tremendously important and extremely remote, and yet much closer, much more directly related to us. There are many things we don't fully understand. And one of them is the extraordinary social complexity of the animals around us. And today I want to tell you a few stories of animal complexity. But first, what do we call complexity? What is complex? Well, complex is not complicated. Something complicated comprises many small parts, all different, and each of them has its own precise role in the machinery. On the opposite, a complex system is made of many similar parts, and it is their interaction that produces a globally coherent behavior. Complex systems have many interacting parts which behave according to simple individual rules, and this results in emergent properties. The behavior of the system as a whole cannot be predicted from the individual rules only. As Aristotle wrote, the whole is greater than the sum of its parts. But from Aristotle, let's move on to a more concrete example of complex system. These are Scottish Terriers. In the beginning, the system is disorganized. Then comes a perturbation, milk. Every individual starts pushing in one direction. And this is what happens. The pinwheel is an emergent property of the interactions between puppies, whose only rule is to try and keep access to the milk, and therefore to push in a random direction. So it's all about finding the simple rules from which complexity emerges. I call this simplifying complexity, and it's what we do at the Chair of Systems Design at ETH Zurich. We collect data on animal populations, analyze complex patterns, try to explain them. It requires physicists to work with biologists, with mathematicians and computer scientists, and it is their interaction that produces cross-boundary competence to solve these problems. So again, the whole is greater than the sum of the parts. In a way, collaboration is another example of complex system. And you may be asking yourself which side I'm on, biology or physics. In fact, it's a little different. And to explain, I need to tell you a short story about myself. When I was a child, I loved to build stuff, to create complicated machines. So I set out to study electrical engineering and robotics. And my end of studies project was about building a robot called ER1, looked like this, that would collect information from its environment and proceed to follow a white line on the ground. It was very complicated, but it worked beautifully in our test room. And on demo day, professors had assembled to grade the project, so we took ER1 to the evaluation room. Turned out the light in that room was slightly different. The robot's vision system got confused. At the first bend in the line, it left its course and crashed into a wall. We had spent weeks building it, and all it took to destroy it was a subtle change in the color of the light in the room. That's when I realized that the more complicated you make a machine, the more likely that it will fail due to something absolutely unexpected. And I decided that, in fact, I didn't really want to create complicated stuff. I wanted to understand complexity, the complexity of the world around us, and especially in the animal kingdom. Which brings us to bats. Beerschen's bats are a common species of European bats. They are very social animals. Mostly they roost or sleep together. And they live in maternity colonies, which means that every spring the females meet after the winter hibernation, and they stay together for about 6 months to rear their young. And they all carry a very small chip, which means that every time one of them enters one of these specially equipped bat boxes, we know where she is. And more importantly, we know with whom she is. So I study roosting associations in bats. And this is what it looks like. During the day, the bats roost in a number of subgroups in different boxes. It could be that on one day, the colony is split between 2 boxes. But on another day, it could be together in a single box, or split between 3 or more boxes. And that all seems rather erratic, really. It's called fission-fusion dynamics, the property for an animal group of regularly splitting and merging into different subgroups. So what we do is take all these data from all these different days and pool them together to extract a long-term association pattern by applying techniques of network analysis to get a complete picture of the social structure of the colony. Okay? So that's what this picture looks like. In this network, all the circles are nodes, individual bats, and the lines between them are social bonds, associations between individuals. Turns out this is a very interesting picture. This bat colony is organized in two different communities which cannot be predicted from the daily fission-fusion dynamics. We call them cryptic social units. Even more interesting, in fact, every year around October, the colony splits up and all bats hibernate separately. But year after year, when the bats come together again in the spring, the communities stay the same. So these bats remember their friends for a really long time. With a brain the size of a peanut, they maintain individualized long-term social bonds. We didn't know that was possible. We knew that primates and elephants and dolphins could do that, but compared to bats, they have huge brains. So how could it be that the bats maintain this complex, stable social structure with such limited cognitive abilities? And this is where complexity brings an answer. To understand this system, we built a computer model of roosting based on simple individual rules and simulated thousands and thousands of days in a virtual bat colony. It's a mathematical model, but it's not complicated. What the model told us is that, in a nutshell, each bat knows a few other colony members as her friends, and is just slightly more likely to roost in a box with them. Simple individual rules. This is all it takes to explain the social complexity of these bats. But it gets better. Between 2010 and 2011, the colony lost more than 2/3 of its members, probably due to the very cold winter. The next spring, it didn't form two communities like every year, which may have led the whole colony to die because it had become too small. Instead, it formed a single, cohesive social unit, which allowed the colony to survive that season and thrive again in the next 2 years. What we know is that the bats are not aware that their colony is doing this. All they do is follow simple association rules, and from this simplicity emerges social complexity, which allows the colony to be resilient against dramatic changes in the population structure. And I find this incredible. Now I want to tell you another story. But for this, we have to travel from Europe to the Kalahari Desert in South Africa. This is where meerkats live. I'm sure you know meerkats. They're fascinating creatures. They live in groups with a very strict social hierarchy. And there is one dominant pair and many subordinates, some acting as sentinels, some acting as babysitters, some teaching pups, and so on. What we do is put very small GPS collars on these animals to study how they move together, and what this has to do with their social structure. And there's a very interesting example of collective movement in meerkats. In the middle of the reserve, which they live in, lies a road. On this road there are cars, so it's dangerous. But the meerkats have to cross it to get from one feeding place to another. So we asked, how exactly do they do this? We found that the dominant female is mostly the one who leads the group to the road. But when it comes to crossing the road, she gives way to the subordinates. A matter of saying, go ahead, tell me if it's safe. What I didn't know, in fact, was what rules in their behavior the meerkats follow for this change at the edge of the group to happen, and if simple rules were sufficient to explain it. So I built a model of simulating meerkats crossing a simulated road. It's a simplistic model. Moving meerkats are like random particles whose unique rule is one of alignment. They simply move together. When these particles get to the road, they sense some kind of obstacle and they bounce against it. The only difference between the dominant female, here in red, and the other individuals is that for her, the height of the obstacle, which is in fact the risk perceived from the road, is just slightly higher. And this tiny difference in the individual rule of movement is sufficient to explain what we observe, that the dominant female leads her group to the road and then gives way to the others for them to cross first. George Box, who was an English statistician, once wrote, "All models are false, but some models are useful." And in fact, this model is obviously false, because in reality, meerkats are anything but random particles. But it's also useful, because it tells us that extreme simplicity in movement rules at the individual level can result in a great deal of complexity at the level of the group. So again, that's simplifying complexity. I would like to conclude on what this means for the whole species. When the dominant female gives way to a subordinate, it's not out of courtesy. In fact, the dominant female is extremely important for the cohesion of the group. If she dies on the road, the whole group is at risk. So this behavior of risk avoidance is a very old evolutionary response. These meerkats are replicating an evolved tactic that is thousands of generations old, and they're adapting it to a modern risk, in this case, a road built by humans. They adapt very simple rules, and the resulting complex behavior allows them to resist human encroachment into their natural habitat. In the end, it may be bats who change their social structure in response to a population crash, or it may be meerkats who show novel adaptation to a human road, or it may be another species. My message here, and it's not a complicated one, but a simple one of wonder and hope. My message here is that animals show extraordinary social complexity, and this allows them to adapt and respond to changes in their environment. So in 3 words, in the animal kingdom, simplicity leads to complexity, which leads to resilience. Thank you.
Thank you very much, Nicola, for this great start. A little bit nervous?
I'm okay, thanks.
Great. I'm sure a lot of people in the audience somehow try to make associations between the animals you were talking about, the bats, meerkats, and humans. You brought some examples. The females are the social ones. The females are the dominant ones. I'm not sure who thinks how, but is it okay to do these associations? Are there stereotypes you can confirm in this regard that can be valid across all species?
Well, I would say there's also counterexamples to these stereotypes. For example, in seahorses or in koalas, in fact, it is the males who take care of the young, always. And the lesson is that it's often difficult and sometimes even a bit dangerous to draw parallels between humans and animals. So that's it, really.
Okay. Thank you very much for this great start. Thank you, Nicola Peroni.